Hello everyone, and welcome back to the channel. Today, we're embarking on an incredible journey through time, exploring one of the most remarkable success stories in the history of computer science. We're talking about Python, the programming language that has captured the hearts of millions of developers worldwide and transformed from a simple hobby project into the dominant force in modern software development. This isn't just a story about code and computers. It's a story about vision, community, perseverance, and how one person's desire to create something better changed the world of technology forever. Our story begins in December 1989, during the cold winter days in Amsterdam, Netherlands. A Dutch programmer named Guido van Rossum found himself with some free time during the Christmas holidays. Like many of us, he was looking for a project to keep himself occupied during the week-long break from work. But unlike most holiday projects that get abandoned after the festivities end, what Guido started during those winter days would go on to revolutionize programming and become one of the most influential pieces of software ever created. Guido worked at the Centrum Wiskunde en Informatica, which is the Dutch National Research Institute for Mathematics and Computer Science. He was an experienced programmer who had worked on various projects and had become increasingly frustrated with the limitations of existing programming languages. You see, in the late 1980s, the programming landscape was quite different from what we see today. Programmers essentially had to choose between two extremes, and neither option was particularly satisfying. On one hand, you had languages like C and C++, which were incredibly powerful and gave programmers complete control over the computer's hardware. These languages were fast and efficient, and you could do almost anything with them. But they were also notoriously difficult to work with. Writing code in C required managing memory manually, dealing with pointers, and wrestling with complex syntax. Even simple programs required dozens of lines of boilerplate code before you could actually start solving your problem. For experienced programmers, this was manageable, but it made programming intimidating and inaccessible to newcomers. It also meant that even simple tasks took a long time to implement, and the resulting code was often difficult to read and maintain. On the other hand, you had simpler scripting languages that were easier to use but severely limited in what they could do. These languages were fine for small tasks, but they weren't suitable for building real applications. Guido had been working with a language called ABC, which was designed specifically to be easy to learn and teach programming. ABC had some really innovative features that made it more intuitive than other languages of the time. It used English-like syntax and had some clever ideas about how to structure code. Guido really appreciated these aspects of ABC and had been involved in its development team. However, ABC has significant problems that made it impractical for real-world use. It wasn't extensible, meaning you couldn't easily add new functionality to the language. It was also too isolated from the operating system, which meant you couldn't use it to write programs that needed to interact closely with the computer's underlying systems. ABC was great as an educational tool, but it wasn't suitable for professional software development. These limitations frustrated Guido because he could see that ABC had the right ideas about making programming more accessible and readable, but it couldn't be used for serious work. Guido had been thinking about these problems for a while. He had been working on a project called Amoeba, which was a distributed operating system designed to make multiple computers work together as if they were one machine. This was cutting-edge research at the time, and Guido needed a scripting language that could interact with the Amoeba system. He had tried using ABC for this purpose, but its limitations made it unsuitable. He needed something better, something that combined the ease of use and readability of ABC with the power and flexibility of languages like C. During that Christmas break, Guido made a decision that would change his life and the world of programming. He decided to create a new programming language that would bridge the gap between simple but limited languages and powerful but complex ones. He wanted to create a language where you could express your ideas clearly and concisely, where the code would be easy to read and understand, but which would also be powerful enough for real applications. He wanted a language that beginners could learn quickly, but that experts would find powerful enough for their most demanding projects. Guido started working on the implementation immediately. He was experienced enough to know that creating a programming language from scratch was a massive undertaking. But he also knew that he could borrow ideas from existing languages and build on what had already been done. He took many concepts from ABC, particularly the idea of using indentation to define code blocks instead of using curly braces or special keywords. This was a controversial choice that would define Python's appearance and become one of its most distinctive features. The idea of using indentation might seem strange if you're not familiar with programming, so let me explain. In most programming languages, when you want to group statements together, you use some kind of delimiter. In C and similar languages, you use curly braces. In other languages, you might use keywords like begin and end, but these delimiters are just for the computer's benefit. Human readers rely on indentation to understand the structure of the code. We naturally indent nested code to make it easier to read. Guido realized that if humans were using indentation to understand code anyway, why not make indentation the actual mechanism that defines structure? This would force programmers to write neatly formatted code and would eliminate the possibility of having code that looks like it does one thing but actually does another, because the indentation doesn't match the delimiters. Guido also decided to make Python object-oriented from the start. Object-oriented programming was becoming increasingly popular in the late 80s, and languages like C++ and Smalltalk had shown the power of this paradigm. In object-oriented programming, you organize code around objects that combine data and the functions that operate on that data. This makes it easier to model real-world concepts in code and helps manage complexity in large programs. However, Guido didn't want to force everything to be object-oriented like some languages did. He wanted Python to support object-oriented programming, but also allow other programming styles when they were more appropriate. Another key decision was to make Python interpreted rather than compiled. In a compiled language, you write your code and then run it through a compiler that translates it into machine code before you can run it. This makes programs run faster, but it adds an extra step to the development process. In an interpreted language, the code is executed directly without a separate compilation step. This makes development faster because you can write code, run it immediately, see the results, and make changes without waiting for compilation. The trade-off is that interpreted programs generally run slower than compiled ones, but Guido felt that the benefits of faster development were more important for most applications. Guido worked intensively on Python throughout that Christmas break and continued developing it in his spare time over the following months. He chose the name Python not because of the snake, as many people assume, but because he was a fan of the British comedy troupe Monty Python. He had grown up watching Monty Python's Flying Circus and loved their absurdist humor. He wanted a name for his language that was short, unique, and slightly mysterious, and Python fit perfectly. This choice reflected Guido's personality and his desire to create something that was not only functional, but also enjoyable to use. The Monty Python connection would influence Python's culture, with official documentation often including references to spam, eggs, and other Monty Python jokes. By February 1991, just over a year after starting the project, Guido felt that Python was ready to share with the world. He posted the first public version, Python 0.90, to a Usenet newsgroup called alt.sources. For younger viewers who might not know, Usenet was like an early version of internet forums, and it was one of the primary ways that programmers shared code before the World Wide Web became popular. Posting to alt.sources meant that any programmer who was interested could download the Python interpreter try it out, and provide feedback. Even this very first public version of Python was remarkably complete. It already had many features that would make it successful. It had the core data types that programmers need, including numbers, strings, lists, and dictionaries. It had functions, which allowed programmers to organize their code into reusable pieces. It had exception handling, which provided a clean way to deal with errors. It supported object-oriented programming with classes and inheritance. And crucially, it had a module system that allowed the language to be extended with new functionality. The module system deserves special attention because it was one of the keys to Python's future success. Guido understood that no matter how good he made the core language, there would always be specialized tasks that needed specialized tools. Rather than trying to build everything into the language itself, which would make it bloated and difficult to learn, he created a system where people could write modules that added new capabilities. These modules could be imported into programs when needed, keeping the core language simple while making unlimited functionality available. This architecture would later enable the creation of the massive ecosystem of Python libraries that exists today. The early response to Python was modest but encouraging. A small group of programmers downloaded it, tried it out, and many of them were impressed. They appreciated the clean syntax and the way Python let them express their ideas clearly. They liked that they could write programs much more quickly in Python than in C, and that the resulting code was much easier to read and understand. Some of these early adopters started using Python for their own projects and contributing feedback and even code back to Guido. Guido set up a mailing list where Python users could discuss the language, share code, ask questions, and suggest improvements. He was very active on this mailing list, responding to questions, explaining his design decisions, and carefully considering suggestions for new features. This open, collaborative approach helped build a sense of community around Python from the very beginning. People felt that they had a voice in the language's development and that Guido genuinely cared about making Python useful for real programmers. However, Guido was also careful about which features he added to Python. He had a clear vision of what he wanted Python to be, and he was willing to say no to suggestions that didn't fit that vision. He wanted Python to remain simple and easy to learn, with ideally one obvious way to do any given task. This philosophy would later be formalized in the Zen of Python, but it guided Guido's decisions from the start. He understood that every feature added to a language makes it more complex and harder to learn, so each addition had to be justified by significant utility. Throughout the early 1990s, Python continued to evolve and improve. Guido released new versions regularly, each adding new features and fixing bugs. In January 1994, a major milestone was reached with the release of Python 1.0. This version included several important additions that had been requested by the growing Python community. It added functional programming tools like lambda, map, filter, and reduce. Lambda allowed programmers to create small anonymous functions on the fly. Map, filter, and reduce provided elegant ways to process lists and other sequences. These features made Python more powerful and expressive without sacrificing its readability. Python 1.0 also solidified many aspects of the language that had been experimental in earlier versions. It represented Guido's statement that Python was ready for serious use, not just experimentation. The release was accompanied by comprehensive documentation and a reference manual that explained all of Python's features in detail. This documentation was important because it made Python accessible to people who hadn't been following its development from the beginning. During this period, Python started to attract attention beyond the small group of early adopters. Word spread through the programming community about this new language that made programming more enjoyable. Programmers who tried Python often became enthusiastic advocates, telling their colleagues about it and using it for their projects whenever possible. This grassroots growth was crucial to Python's success. Unlike some programming languages that were backed by large companies with marketing budgets, Python grew purely through word of mouth and the enthusiasm of its users. One factor that helped Python's growth was the emergence of the World Wide Web in the mid-90s. As the web became popular, there was suddenly a huge demand for programming tools that could work with web technologies. Python was well suited for web programming because it was good at processing text and working with internet protocols. Early web developers discovered that they could use Python to create dynamic websites, process form data, and build web applications much more easily than with other available tools. This gave Python a foothold in an exciting new area of computing that was experiencing explosive growth. In 1995, something important happened that would significantly impact Python's development. Guido van Rossum moved to the Corporation for National Research Initiatives, known as CNRI, in Reston, Virginia. CNRI was a nonprofit organization that conducted research and development in information technology. At CNRI, Guido was given the resources and support to work on Python more extensively. He was no longer developing Python entirely in his spare time. Now he had institutional backing and could dedicate more of his working hours to improving the language. At CNRI, a team began to form around Python's development. While Guido remained the primary architect and decision-maker, he now had other talented developers helping with implementation, testing, and documentation. This allowed Python's development to accelerate significantly. The team at CNRI began thinking about how to make Python suitable for larger-scale applications and how to improve its performance and capabilities. They also worked on porting Python to different platforms, ensuring that it could run on various operating systems and computer architectures. During the late 90s, Python's capabilities expanded significantly. New modules were added to the standard library, giving Python programmers ready-made tools for common tasks. The language itself continued to be refined, with improvements to its syntax and semantics. The community continued to grow, with more programmers discovering Python and contributing to its ecosystem. By the end of the decade, Python had gone from being an obscure hobby project to a legitimate programming language with thousands of users worldwide. In October 2000, Python reached another major milestone with the release of version 2.0. This was a significant update that added important new features and represented a maturation of the language and its development process. Python 2.0 introduced list comprehensions, which provided an elegant and efficient way to create new lists based on existing lists. This feature became hugely popular because it allowed complex list processing to be expressed in a single, readable line of code. Python 2.0 also introduced a garbage collector that could detect and clean up circular references. In earlier versions of Python, certain patterns of object references could cause memory leaks because the reference counting system couldn't detect them. The new garbage collector solved this problem, making Python more robust for long-running applications. This was an important step toward making Python suitable for enterprise software that needed to run continuously without memory problems. Perhaps most significantly, Python 2.0 marked a change in how Python was developed. The development process became much more open and transparent. The source code was moved to a public repository where anyone could see the latest changes. A public bug tracker was established where users could report problems and track their resolution. Proposals for major changes to the language, called Python Enhancement Proposals or PEPs, were published for community discussion before being implemented. This transparency helped build trust in Python and encouraged more people to contribute to its development. The PEP process deserves special mention because it became a model for how open-source projects could manage their evolution. When someone had an idea for a significant change to Python, they would write a PEP document explaining the problem, proposing a solution, discussing alternatives, and addressing potential concerns. This document would be published and discussed by the community. Guido would read the discussion and make a final decision about whether to accept, reject, or request modifications to the proposal. This process ensured that major changes were carefully considered and that the community had input into Python's direction. Around the turn of the millennium, Python began finding its niche in several important domains. One of these was scientific computing. Scientists and researchers discovered that Python was ideal for their needs. They could write scripts to process experimental data much more quickly than in compiled languages. And the code was easy to share with colleagues who could understand it even if they weren't expert programmers. The interactive Python interpreter was particularly useful for exploratory data analysis, allowing scientists to try different approaches and immediately see the results. This led to the development of NumPy, a library that provided efficient arrays and mathematical operations for Python. NumPy was built on earlier efforts called Numeric and NumArray, which had shown the potential for using Python for numerical computing. NumPy provided capabilities similar to MATLAB, a commercial scientific computing environment, but with the advantages of Python's general-purpose programming features and open-source licensing. This made Python an attractive alternative to expensive proprietary tools for academic and research institutions. Following NumPy came SciPy, which added even more scientific computing capabilities, including optimization, integration, interpolation, signal processing, and statistics. Together, NumPy and SciPy transformed Python into a powerful platform for scientific computing. Universities and research institutions around the world began adopting Python for their computational needs. This created a virtuous cycle where more scientists using Python led to more scientific libraries being created, which made Python even more attractive for scientific work. Another domain where Python found early success was system administration and automation. System administrators, the people responsible for keeping computer systems and networks running, discovered that Python was perfect for writing scripts to automate repetitive tasks. Its ability to interact easily with the operating system, process text, and work with files made it ideal for tasks like log file analysis, backup automation, and system monitoring. Python scripts were much easier to write and maintain than shell scripts for complex tasks, and they worked consistently across different operating systems. Web development was another area where Python began to make significant inroads. In 2005, a web framework called Django was released, and it would have a major impact on Python's popularity. Django was created by developers at a newspaper who needed to build web applications quickly and reliably. They built a framework that followed Python's philosophy of having clear, obvious ways to do things, and they included many features that web developers commonly needed, like database integration, user authentication, and an administrative interface. Django's slogan was, "The web framework for perfectionists with deadlines," and it lived up to that promise. Developers found that they could build complex, database-driven websites in a fraction of the time it would take with other tools. Django came with excellent documentation and followed best practices for security and performance. It quickly became one of the most popular web frameworks in any language. Major websites like Instagram, Pinterest, and the Washington Post would eventually be built with Django, demonstrating that Python could handle even the most demanding web applications. Around the same time, other Python web frameworks were emerging. TurboGears combined several existing Python components into a full-featured framework. Later, Flask was created as a lighter-weight alternative for developers who wanted more flexibility and didn't need all of Django's features. Pyramid, Bottle, and other frameworks also emerged, each with different philosophies and target use cases. This diversity of web frameworks meant that Python developers could choose the tool that best fit their specific needs. Google was an early corporate adopter of Python, and their endorsement significantly boosted Python's credibility. Google used Python extensively in their infrastructure, and they even had a motto that reportedly said, "Python, where we can, C++, where we must." This reflected the reality that Python was productive and pleasant to work with for most tasks, with performance-critical components written in faster compile languages when necessary. In 2005, Google hired Guido van Rossum himself, giving him the freedom to spend half his time working on Python development. This was a strong signal that Python was being taken seriously by one of the world's leading technology companies. YouTube, which was acquired by Google in 2006, was largely built with Python. The fact that one of the internet's largest and most trafficked websites ran on Python demonstrated that the language could scale to handle enormous workloads. While Python wasn't the fastest language, its productivity advantages and the ability to optimize critical paths meant that it could power even the most demanding applications. This example inspired many other companies to consider Python for their own projects. Now we come to one of the most important and controversial chapters in Python's history: the development and release of Python 3. In December 2008, Python 3.0 was released. This was not just another incremental update. It was a major revision of the language that intentionally broke backward compatibility with Python 2. This means that code written for Python 2 would not necessarily work in Python 3 without modifications. For a programming language, this is a drastic step. Programming languages typically go to great lengths to maintain backward compatibility because breaking existing code is extremely disruptive for users. So why did Guido and the Python development team make this controversial decision? The answer is that they wanted to fix fundamental design issues and remove cruft that had accumulated over Python's first 2 decades. When Python was first created, Guido had made some design decisions that seemed reasonable at the time, but had turned out to be problematic. For example, in Python 2, there were both str and Unicode types for handling text, which created confusion and bugs. There were old-style and new-style classes, creating 2 different object systems. The print statement, which had been in Python from the beginning, was inconsistent with the rest of the language because it was a statement rather than a function. The Python developers decided that it was better to fix these issues once and deal with the disruption than to carry them forward forever. They planned Python 3 carefully, trying to make the migration as smooth as possible. They provided tools that could automatically convert much Python 2 code to Python 3. They documented all the changes extensively, and they committed to maintaining Python 2 for a long time to give people time to migrate. Python 2.7, released in 2010, was designated as the final version of Python 2 and would be supported until January 1st, 2020, giving users a decade to transition. Despite these efforts, the transition to Python 3 was painful and took much longer than anyone expected. Many organizations had large code bases written in Python 2, and migrating them to Python 3 required significant time and effort. Some popular third-party libraries were slow to support Python 3, creating a chicken and egg problem where people couldn't switch to Python 3 because their needed libraries weren't available. And library developers didn't prioritize Python 3 support because many users were still on Python 2. For several years, the Python community was effectively split, with both versions being actively used. The changes in Python 3, while disruptive, did make the language better. Strings and bytes were cleanly separated, eliminating a major source of bugs. Print became a function, making it consistent with the rest of the language and more flexible. Integer division returned a float by default, matching mathematical expectations. The standard library was reorganized to be more consistent and logical. The language was cleaned up in countless small ways that removed inconsistencies and duplicate ways of doing things. These improvements made Python 3 a better language than Python 2, but it took years for the ecosystem to fully catch up. While the Python 2 to 3 transition was happening, something else was occurring that would dramatically impact Python's future. The fields of data science, machine learning, and artificial intelligence were experiencing explosive growth, and Python was perfectly positioned to become the dominant language in these areas. The combination of Python's ease of use, the powerful numerical libraries like NumPy and SciPy, and new libraries specifically designed for data analysis and machine learning, made Python the obvious choice for practitioners in these fields. In 2008, the same year Python 3 was released, a library called Pandas was created by Wes McKinney. Pandas provided data structures and tools for data analysis that were inspired by R, a programming language popular in statistics. Pandas made it easy to load, clean, transform, and analyze data, tasks that are central to data science. The data frame, Pandas' core data structure, became ubiquitous in data analysis workflows. Data scientists could now do sophisticated data manipulation in Python that previously required specialized tools or extensive custom code. Matplotlib, a plotting library for Python, provided capabilities for creating publication-quality visualizations. Based on MATLAB's plotting interface, Matplotlib allowed researchers and analysts to create charts, graphs, and visualizations to understand and communicate their findings. Later, libraries like Seaborn built on Matplotlib to make creating attractive statistical graphics even easier. The combination of Pandas for data manipulation and Matplotlib for visualization gave Python capabilities that rivaled or exceeded specialized data analysis environments. Machine learning libraries were the next piece of the puzzle. Scikit-learn, first released in 2007 and reaching maturity in the early 2010s, provided implementations of all the standard machine learning algorithms in a consistent, easy-to-use interface. Researchers and practitioners could try different machine learning approaches on their data with just a few lines of code. Scikit-learn came with excellent documentation and examples, making machine learning accessible to a much broader audience than just specialists. The real explosion came with deep learning, the branch of machine learning that uses neural networks with many layers to learn complex patterns from data. Deep learning has achieved remarkable results in areas like image recognition, natural language processing, and game playing, often matching or exceeding human performance. When Google released TensorFlow in 2015, they chose Python as the primary interface language. TensorFlow provided the tools needed to build and train deep neural networks, and making it accessible through Python meant that researchers could experiment with these powerful techniques using a language they already knew. Facebook followed with PyTorch in 2016. PyTorch became especially popular in the research community because of its flexible, intuitive interface that matched Python's philosophy of readability and ease of use. The competition between TensorFlow and PyTorch drove both to improve, benefiting the entire community. Other deep learning frameworks like Keras, which provided a high-level interface that could run on top of TensorFlow or other backends, further lowered the barriers to working with neural networks. Python's dominance in artificial intelligence and data science cannot be overstated. When researchers publish papers about new AI techniques, they almost always include Python implementations. When companies build machine learning systems to recommend products, detect fraud, or optimize operations, they typically use Python. When students learn about neural networks and machine learning, they learn with Python. This created a massive surge in Python's popularity, bringing in millions of new users who might never have learned programming otherwise. Education has been another major driver of Python's growth. Computer science educators realized that Python was an ideal first language for teaching programming. Its clear syntax meant that students could focus on learning programming concepts without getting bogged down in complex syntax rules. A beginner could write their first meaningful Python program in a single class session, something that was impossible with languages like Java or C++ that required understanding classes, types, access modifiers, and other advanced concepts just to write Hello World. Universities around the world adopted Python for their introductory programming courses. MIT switched from Scheme to Python for their famous Introduction to Computer Science course. Other prestigious universities followed suit. High schools teaching computer science also adopted Python. The result was that millions of students learned programming through Python, and many of them continued using it throughout their careers. This created a massive pipeline of Python programmers entering the workforce every year. Online education platforms amplified this effect. Websites like Codecademy, Coursera, edX, DataCamp, and many others offered Python courses that anyone with an internet connection could take. These courses reached people who might never have considered learning programming, including scientists, analysts, entrepreneurs, and hobbyists. Python's approachability made it possible for people without a computer science background to learn programming and use it in their own fields. A biologist could learn Python to analyze genetic data. A marketer could learn Python to analyze customer behavior. An artist could learn Python to create generative art. The Python Package Index, or PyPI, played a crucial role in Python's ecosystem. PyPI is a repository where developers can upload Python packages and where others can easily download and install them. By 2025, PyPI hosted hundreds of thousands of packages covering virtually every imaginable domain. Need to scrape data from websites? There's a package for that, called Beautiful Soup or Scrappy. Need to work with images? There's Pillow. Need to build games? There's Pygame. Need to work with Excel files? There's OpenPixel. Whatever you want to do in Python, there's probably already a package that helps you do it. The pip tool made installing packages trivially easy. Instead of manually downloading files, managing dependencies, and configuring installation paths, a Python programmer could simply type pip install package name and have everything set up automatically. This ease of installation was a major improvement over what was required for libraries in many other languages. It lowered the barrier to using sophisticated functionality and encouraged developers to share their code as packages rather than keeping it private. The community around Python has been one of its greatest strengths. Python conferences called PyCons are held around the world, providing opportunities for Python programmers to meet, learn, and share ideas. The original PyCon started in 2003 in the United States and has grown into a major event with thousands of attendees. Regional PyCons now happen on every continent, fostering local Python communities. These conferences have been notable for their inclusivity, implementing codes of conduct to ensure welcoming environments, and providing financial aid to help people attend who couldn't otherwise afford it. Online, the Python community is vibrant and helpful. Stack Overflow, the popular question and answer site for programmers, has millions of Python-related questions and answers. When a programmer encounters a problem, there's a good chance someone else has encountered it before and that the solution is already documented. The Python subreddit, Discord servers, IRC channels, and other online forums provide spaces where Python programmers can get help, share projects, and discuss the language. This helpful community has made learning Python easier and has contributed to its continued growth. Throughout Python's history, several key people beyond Guido have made major contributions. Tim Peters, who joined Guido at CNRI and later moved with him to other companies, has been influential in both the philosophy and implementation of Python. He wrote The Zen of Python, a collection of 19 aphorisms that capture Python's design philosophy. These range from "beautiful is better than ugly" to there should be one and preferably only one obvious way to do it. 2. Namespaces are one honking great idea. Let's do more of those. The Zen of Python is actually included in Python itself and can be viewed by typing import this in the Python interpreter. Barry Warsaw has been a core Python developer since the 90s and has made important contributions to many aspects of the language, particularly email handling and the development process. Brett Cannon has been instrumental in Python's development for over 2 decades and was particularly important during the Python 2.3 transition. He worked on tools to help people migrate their code and wrote extensively about the process. Nick Coughlin has been a core developer since the mid-2000s and has contributed to many areas, including the import system, standard library, and Python enhancement proposals. In 2018, something unexpected happened. After nearly 30 years of leading Python's development, Guido van Rossum announced that he was stepping down as Python's benevolent dictator for life, or BDFL as he was affectionately known. The final decision that led to this was about a feature called assignment expressions, or the walrus operator, which allows variable assignment within expressions. The debate about this feature became heated, and Guido realized that the responsibility of making final decisions on controversial issues had become too stressful. He felt it was time for Python to transition to a new governance model. The Python community responded by creating a new governance structure. They formed a 5-person steering council elected by the core developers. The first steering council, elected in early 2019, included Barry Warsaw, Brett Cannon, Carol Willing, Guido van Rossum himself, and Nick Coughlin. Yes, Guido remained on the council, but now as one voice among 5 rather than having the final say on everything. This transition demonstrated the maturity of the Python community and ensured that Python's development would continue smoothly without depending on any single person. Guido's journey after stepping down as BDFL has been interesting. He spent some time at Dropbox, where he had moved from Google in 2013. In October 2019, he announced his retirement, but retirement didn't last long. In November 2020, Guido announced that he was coming out of retirement to join Microsoft's developer division. At Microsoft, he continues to work on improving Python, particularly focusing on performance. His involvement shows that, even after stepping back from leadership, he remains committed to the language he created. Python's rise in popularity through the 2010s and into the 2020s has been remarkable. In 2018, Python became the most taught programming language in universities, surpassing Java, which had held that position for years. In 2019, Python overtook Java on the GitHub platform in terms of pull requests, indicating strong developer activity. In 2021, Python reached #1 position in the TIOB index, which ranks programming languages based on search engine results, tutorial counts, and other factors. Python has maintained this top position, reflecting its use across virtually every domain of programming. What makes Python's success particularly impressive is its breadth. It's not just dominant in one area. Python is widely used in web development, with frameworks like Django, Flask, and FastAPI powering websites and APIs. It's the undisputed leader in data science and machine learning, with libraries like NumPy, Pandas, scikit-learn, TensorFlow, and PyTorch. It's popular for automation and scripting, for scientific computing, for education, for game development with Pygame, for desktop application development with libraries like PyQt and tkinter, for embedded systems and IoT devices with MicroPython and CircuitPython. Major technology companies rely heavily on Python. Instagram, one of the world's largest social media platforms with billions of users, is built primarily with Python and Django. When Instagram engineers give talks about their technical infrastructure, they emphasize how Python's productivity and the vast ecosystem of libraries have been crucial to their ability to scale. Netflix uses Python extensively throughout their organization, From their recommendation engine to their infrastructure management tools, they've even created their own Python libraries and share them with the community. Spotify uses Python for data analysis and back-end services. Dropbox desktop client is written in Python, and they've made significant contributions to Python's development, including hiring Guido van Rossum for several years. NASA uses Python for scientific calculations, data analysis, and even in spacecraft operations. The Mars rovers have used Python in their mission operations software. Financial institutions use Python for quantitative analysis, risk management, and algorithmic trading. The ease of expressing complex mathematical operations in clear code makes Python ideal for financial modeling. In the sciences, Python has become ubiquitous. Astronomers use Python to analyze data from telescopes and spacecraft. The Event Horizon Telescope team that captured the first image of a black hole used Python for much of their data processing and analysis. Particle physicists at CERN use Python to analyze data from the Large Hadron Collider. Biologists use Python for genomic analysis and bioinformatics. Chemists use Python for molecular modeling and analysis. Climate scientists use Python to analyze climate data and create models. Python's integration capabilities have been another factor in its success. When Python's interpreted nature makes it too slow for performance-critical operations, programmers can write those sections in C or C++ and call them from Python. This gives Python the productivity advantages of a high-level language while still achieving the performance of compiled languages when necessary. Libraries like NumPy, which is crucial for numerical computing, are actually implemented in C under the hood but present a Python interface. This architecture provides the best of both worlds. Tools have emerged to make Python faster in various ways. PyPy is an alternative implementation of Python that uses just-in-time compilation to achieve significant performance improvements for many programs. Cython is a tool that compiles Python code to C, allowing performance-critical sections to be optimized. Numba is another tool that can compile Python functions to machine code at runtime, dramatically speeding up numerical computations. These tools mean that Python programs can be optimized when necessary without abandoning the language entirely. Python's development continues actively with new versions released regularly. The release cycle has been standardized, with a new minor version coming out annually, and each version receiving bug fixes and security updates for 5 years. Python 3.9, released in October 2020, added dictionary merge operators and type hinting improvements. Python 3.10, released in October 2021, added structural pattern matching, a powerful feature that allows elegant handling of complex conditional logic. Python 3.11, released in October 2022, focused on performance improvements and better error messages. Python 3.12, released in October 2023, brought more performance improvements and cleaned up some legacy features. Work continues on Python 3.13 and beyond, with ongoing efforts to improve performance, add useful features, and make the language even better. One major project is working to remove or make optional the Global Interpreter Lock, or GIL, which currently prevents Python from fully utilizing multiple CPU cores in threaded programs. Removing the GIL is a complex undertaking that requires careful work to maintain Python's stability and compatibility, but it would significantly improve Python's performance for certain types of applications. The Python Software Foundation, or PSF, plays an important role in Python's ecosystem. Established in 2001, the PSF is a non-profit organization dedicated to promoting, protecting, and advancing the Python programming language and supporting and facilitating the growth of the international community of Python programmers. The PSF holds the intellectual property rights to Python, manages the trademark, and provides financial support for Python-related projects and events. They fund development work, sponsor conferences, provide grants to community organizers, and support diversity initiatives. The PSF has been progressive in promoting diversity and inclusion in the Python community. They've supported programs like PyLadies, which provides a supportive community for women and gender minorities in Python. They've funded workshops and outreach programs in underrepresented communities. They've provided financial assistance to help people from diverse backgrounds attend conferences and participate in the community. This focus on inclusion has helped make Python's community more welcoming and diverse than many other programming language communities. Python's documentation has always been one of its strengths. The official Python documentation is comprehensive, well organized, and includes numerous examples. The Python tutorial, which is part of the official documentation, provides an excellent introduction to the language for beginners. Each module in the standard library has detailed documentation explaining its functions, classes, and usage patterns. This high-quality documentation has been crucial to Python's adoption because it makes learning the language and using its features much easier. Beyond official documentation, the Python community has created an enormous amount of educational content. There are thousands of Python books covering everything from absolute beginner guides to advanced topics like metaprogramming and optimization. There are YouTube channels dedicated to Python tutorials with millions of subscribers. There are blogs, podcasts, and websites devoted to Python. This wealth of educational resources means that no matter your learning style or experience level, there are resources available to help you learn Python. Python's influence extends beyond just the programs written in it. The language's philosophy and design have influenced other programming languages. Languages like Ruby share Python's emphasis on readability and programmer happiness. Swift, Apple's programming language, borrowed ideas about optionals and other features from Python. Go, created at Google, shares Python's emphasis on simplicity and having one obvious way to do things. Even languages that predate Python have added features inspired by it. The fact that Python has influenced other languages demonstrates how impactful its design decisions have been. The culture around Python is also distinctive. The emphasis on readability and the Zen of Python's principles have created a culture where Python programmers care about writing clean, maintainable code. The term Pythonic is used to describe code that follows Python's conventions and idioms. Code that is not just correct, but also elegant and idiomatic. Python programmers often engage in discussions about the most Pythonic way to solve a problem, reflecting a cultural value of not just solving problems, but solving them well. Python enhancement proposals, or PEPs, have become more than just a technical mechanism for proposing changes. They're a form of technical communication that has been adopted by other projects. PEPs document not just what was decided, but why, including discussions of alternatives and trade-offs. This creates a valuable historical record that helps people understand Python's evolution. Some PEPs, like PEP 8, which defines Python's style guide, have become fundamental references that every Python programmer should know. The asynchronous programming capabilities added to Python in recent versions deserve special mention. Python 3.4 introduced the Asyncio module, and Python 3.5 added async and await syntax. These features allow Python to handle concurrent operations efficiently, which is important for applications like web servers that need to handle many simultaneous connections. While asynchronous programming adds complexity, Python's implementation aims to make it as approachable as possible. Libraries like FastAPI have leveraged these capabilities to create extremely performant web frameworks. Type hints, introduced in Python 3.5, represent an interesting evolution in Python's design. Python has always been dynamically typed, meaning you don't need to declare the types of variables. This makes code more concise and flexible, but can also lead to bugs when functions receive unexpected types. Type hints allow programmers to optionally annotate their code with type information. These hints can be checked by tools like MyPy to catch type-related errors before the code runs. Importantly, type hints are optional, so programmers can use them when helpful, but aren't forced to use them everywhere. The balance between adding powerful features and maintaining simplicity has been an ongoing challenge throughout Python's evolution. Each new feature makes the language more capable, but also more complex to learn completely. The Python development team has tried to handle this by making advanced features optional, so beginners can be productive without learning everything, while advanced users have powerful tools available when needed. The use of decorators, context managers, generators, and other advanced features is not required to write useful Python programs, but they are available when you need them. Python's role in education extends beyond just teaching programming. It's increasingly used as a tool for teaching other subjects. Math teachers use Python to help students visualize mathematical concepts and solve problems. Science teachers use Python to help students analyze experimental data. Art teachers use Python to introduce students to generative art. The accessibility of Python makes it a versatile tool that can enhance education across many disciplines. Students can focus on learning the subject matter while using Python as a tool rather than struggling with complex programming syntax. The Python community has created specialized distributions for different use cases. Anaconda is a distribution focused on data science that includes Python along with hundreds of popular scientific packages pre-installed. It also includes tools for managing environments and installing packages, solving some of the complexity of setting up a data science workstation. MicroPython and CircuitPython are implementations of Python designed to run on microcontrollers and embedded devices, bringing Python to the world of physical computing and IoT devices. These specialized distributions have expanded Python's reach into new domains. Python's testing culture is another strength. The standard library includes the unit test module for writing tests, and third-party tools like PyTest have made testing even easier and more powerful. The Python community strongly encourages writing tests for code, and many projects have extensive test suites. This culture of testing has contributed to Python's reputation for reliability and has helped large Python projects remain maintainable as they grow. The ease of writing tests in Python removes excuses for not testing and promotes better software engineering practices. Virtual environments, which allow Python programmers to create isolated environments with different package versions, have solved one of the classic problems in software development: dependency management. Different projects often need different versions of packages, and virtual environments allow these to coexist on the same computer without conflicts. Tools like Venv, VirtualEnv, and Conda make creating and managing virtual environments straightforward. This capability is crucial for professional Python development and has contributed to Python's suitability for enterprise applications. Python's impact on individual careers has been profound. Countless programmers have found employment because of Python skills. The language's popularity means there are many job opportunities for Python developers across various industries. Data scientists, machine learning engineers, web developers, automation engineers, and many other roles frequently require or prefer Python knowledge. For career switchers, Python's relatively gentle learning curve makes it an accessible entry point into programming careers. Many boot camps teaching programming focus heavily on Python for this reason. The economic impact of Python is difficult to quantify, but undoubtedly enormous. Python powers businesses ranging from startups to some of the world's largest technology companies. The productivity improvements from using Python instead of more verbose languages translate directly into cost savings and faster time to market. The vibrant ecosystem of open-source Python packages represents countless hours of development work that companies can use for free. The Python Software Foundation has estimated that there are millions of Python developers worldwide, and the economic activity they engage in represents billions of dollars. Looking at specific success stories helps illustrate Python's impact. Instagram, as mentioned earlier, is one of the world's largest Python deployments. Despite conventional wisdom that Python couldn't scale to handle billions of users, Instagram's engineers have proven otherwise through careful optimization and smart architecture. They've shared their experiences and tools with the community, contributing back to the ecosystem that enabled their success. Their experience shows that language choice is less important than good engineering practices. Dropbox is another company that has bet heavily on Python. Their desktop client, which runs on millions of computers worldwide, is written primarily in Python. They even hired Guido van Rossum to help them with Python-related challenges. Dropbox has contributed significantly to Python's development, including work on type hints and static analysis tools. Their success demonstrates that Python can be used effectively for client-side applications, not just server-side code. Reddit, the popular social news and discussion website, was originally written in Python. While they've since rewritten some components in other languages for performance reasons, Python remains central to their infrastructure. The founders chose Python in part because of its rapid development capabilities, allowing them to iterate quickly in the early days. This pattern of using Python to get a product to market quickly and then optimizing specific components later has been followed by many successful startups. In the scientific community, Python has enabled discoveries and research that might not have been possible otherwise. The accessibility of powerful computational tools through Python packages has democratized scientific computing. Researchers who previously would have needed to be expert programmers to analyze their data can now use Python with relatively modest programming skills. This has accelerated research across fields, from genomics to astrophysics to climate science. The first image of a black hole, announced in April 2019, was a landmark achievement that involved analyzing petabytes of data from radio telescopes around the world. The team working on this project used Python extensively for their data processing and image reconstruction. They chose Python because of the powerful libraries available and because it allowed collaboration between team members with varying levels of programming expertise. This high-profile success story showcased Python's capabilities to a global audience. Python's role in artificial intelligence and machine learning continues to grow more important. As AI becomes increasingly central to technology and society, Python's position as the primary language for AI development makes it more influential. The recent explosion of interest in large language models, image generation systems, and other AI applications has driven another surge in Python adoption. Researchers and engineers working on these cutting-edge technologies almost universally use Python. The tools and frameworks they create further strengthen Python's ecosystem. The challenges Python faces should not be ignored. Performance remains a concern for some applications. While Python's performance is adequate for many use cases, and while there are ways to optimize performance-critical code, there are domains where Python's speed limitations are significant. Languages like Rust and Go have attracted users in areas where performance is paramount. However, Python's response has been to focus on making it easy to integrate with high-performance code written in other languages, rather than trying to compete on raw speed. The Python 2.3 transition, while ultimately successful, was painful and left some users with a negative impression. Some organizations spent years on migration projects, and during that time, being split between two incompatible versions of the language was a real problem. The Python development team has learned from this experience and is now much more cautious about backward compatibility. Future versions of Python are unlikely to make breaking changes on the scale of Python 3. Competition from newer languages is another challenge. Languages like Go, Rust, Swift, and Kotlin have attracted enthusiastic communities and offer different trade-offs in terms of performance, safety, and expressiveness. Some developers are drawn to these alternatives, particularly for systems programming or performance-critical applications. However, Python's broad ecosystem, large community, and continued development mean it remains competitive across most domains. The complexity of the modern Python ecosystem can be overwhelming for newcomers. With hundreds of thousands of packages available, multiple ways to manage environments, various testing frameworks, and different approaches to common tasks, getting started can be confusing. The Python community has recognized this and has worked to create better onboarding experiences, clearer documentation, and more opinionated guides that help newcomers navigate choices. However, managing this complexity while preserving Python's flexibility remains an ongoing challenge. Despite these challenges, Python's future looks bright. The language continues to evolve and improve with each release. The community remains vibrant and welcoming. The ecosystem of libraries and tools continues to expand. New domains continue to adopt Python, from quantum computing with libraries like Qiskit to cryptocurrency and blockchain development. As new technologies emerge, Python is often among the first languages to have good support for them. The work on removing the global interpreter lock, which has been called the Galactomy project, could significantly impact Python's future. If successful, it would allow Python programs to better utilize modern multi-core processors, addressing one of Python's long-standing performance limitations. This is a multi-year project that requires extensive testing and validation, but it represents the kind of fundamental improvement that could keep Python competitive for decades to come. Python's influence on programming education continues to expand. More schools at all levels are teaching programming, and Python is often the language of choice. Countries are adding programming to their national curricula, frequently choosing Python. This means that millions of young people are growing up with Python as their first programming language. These digital natives will carry Python with them into their careers, whatever fields they enter. This educational momentum suggests Python's popularity will continue for a long time. The role of Python in addressing global challenges should not be underestimated. Climate scientists use Python to model climate change and analyze environmental data. Medical researchers use Python to analyze genomic data and develop new treatments. Epidemiologists used Python extensively during the COVID-19 pandemic to model disease spread and evaluate interventions. Social scientists use Python to analyze large datasets about human behavior and society. Python has become a tool not just for building software products, but for understanding and solving important problems facing humanity. The open-source nature of Python has been fundamental to its success. Anyone can download Python, use it for any purpose, examine its source code, and even contribute improvements. This openness has built trust and encouraged adoption. Organizations know that they're not dependent on a single company's decisions about Python's future. The transparent development process means anyone can participate in shaping Python's direction. This democratic approach to language development has created a strong sense of community ownership. Python's story is ultimately about more than just a programming language. It's about how good design, community engagement, and strategic positioning can create something that transcends its original purpose. Guido van Rossum wanted to create a better tool for his own work, but he created something that has empowered millions of people worldwide. He wanted to make programming more accessible, and Python has brought programming to people who never would have considered it otherwise. He wanted to create something that would be useful, and Python has become essential to modern technology. The lessons from Python's history are valuable for anyone creating technology or building communities. The importance of having a clear vision and principles cannot be overstated. Python's success came in large part from Guido's clear idea of what he wanted Python to be and his willingness to say no to features that didn't fit that vision. The value of community and open collaboration is another key lesson. Python grew because people shared it, contributed to it, and evangelized it. No amount of marketing could have created the grassroots enthusiasm that drove Python's adoption. The importance of timing and context is also evident. Python succeeded in part because it arrived when the internet was becoming mainstream, providing opportunities for web development. It thrived in data science because it was well positioned when that field exploded. It dominated AI because it was already the language of scientific computing when deep learning emerged. Being in the right place at the right time matters, but you also have to be ready to seize opportunities when they arise. Persistence and long-term thinking have been crucial to Python's success. It took decades for Python to reach its current level of popularity. There were periods when growth was slow, when competing languages seemed more popular, when the future was uncertain. But the Python community kept improving the language, building libraries, teaching people, and solving problems. This long-term commitment and the willingness to invest in the future paid off enormously. As we look to the future, Python seems poised to remain important for years to come. The transition to Python 3 is complete, providing a stable foundation. The language continues to improve with each release. The ecosystem is mature, but still growing. The community is large, active, and welcoming. New use cases continue to emerge. While it's impossible to predict the future with certainty, all signs point to Python remaining a major force in programming. The story of Python reminds us that individuals can make a difference. One person, working during a Christmas holiday, created something that changed the world. Guido van Rossum didn't have the resources of a large company or a team of developers when he started. He just had an idea, the skills to implement it, and the determination to see it through. His creation has enabled scientific discoveries, powered major companies, educated millions of people, and empowered countless individuals to bring their ideas to life through code. Python's legacy extends beyond the programs written in it. It has influenced how we think about programming language design, showing that simplicity and readability are not just nice to have, but can be key advantages. It has demonstrated the power of open-source development and community-driven evolution. It has proven that a language can be both easy to learn and powerful enough for sophisticated applications. It has shown that technical excellence combined with community engagement can overcome challenges and achieve lasting success. For those of us who use Python, whether we're beginners writing our first programs or experts building complex systems, we're part of this remarkable story. Every time we write Python code, we're standing on the shoulders of giants, using a tool that represents decades of thought, work, and collaboration by thousands of people. We're part of a community that spans the globe and includes people from every background imaginable. We're using a language that embodies the idea that technology should be accessible, understandable, and empowering. As we conclude this journey through Python's history, it's worth taking a moment to appreciate how far we've come. From a hobby project started during a Christmas break in 1989 to the most popular programming language in the world today, Python's rise has been extraordinary. It has survived challenges, adapted to changes, and continued to grow. It has brought programming to millions of people who might never have tried it otherwise. It has powered innovations that have changed how we live, work, and understand the world. The future will bring new challenges and opportunities. Technology will continue to evolve. New paradigms will emerge, and requirements will change. But if Python's history has taught us anything, it's that the combination of good design, strong community, and willingness to evolve can overcome challenges and create lasting value. Whatever the future holds, Python and its community seem well prepared to face it. Thank you so much for joining me on this deep dive into the extraordinary history of Python. I hope you've gained a new appreciation for this remarkable programming language and the people who created it. If you enjoyed this video, please hit that like button. Subscribe to the channel for more content about programming, technology, and computer science history. Drop a comment below telling me about your experiences with Python. When did you first learn it? What do you use it for? What's your favorite thing about Python? I love hearing from you all and learning about your journeys with programming. If you want to learn more about Python, I'll put some links in the description to great resources for beginners and advanced users alike. The official Python documentation is excellent, and there are countless tutorials, courses, and books available. The Python community is incredibly welcoming, so don't hesitate to get involved, ask questions, and start contributing. Remember, every expert was once a beginner, and every great program started with someone deciding to try. Python makes that first step easier than almost any other language. Whether you want to analyze data, build websites, create games, automate boring tasks, or just understand how programming works, Python is an excellent choice. The same language that powers Instagram and Netflix is accessible to complete beginners. That's the magic of Python. Until next time, keep coding, keep learning, and keep exploring the amazing world of technology. The story of Python shows us that with vision, dedication, and community, we can create things that change the world. Who knows? Maybe the project you start today will be the next great success story we'll be talking about decades from now. See you in the next video. And happy coding, everyone.